Hello, my name is Joel, and I'll be presenting our ObjectNav submission from our work, Auxiliary Tasks and Exploration Enable ObjectNav. Object-goal navigation tasks the agent with searching for and stopping at an instance of a goal category, such as a stool, in an unseen environment. The agent is provided RGPD and GPS and compass sensors for localization. Our work investigates how we can accomplish ObjectNav through large-scale reinforcement learning training of neural agents with generic architectures, that is, an agent which embeds its observations, concatenates them, and aggregates them in an RNN. This kind of agent nearly solves the simpler embodied navigation task, PointNav, through a large-scale training technique introduced in DDPPO. However, in ObjectNav, naive scaling leads to only 6% success rates. This has led previous efforts, including both of the winners of the previous iteration of this challenge, towards semi-analytic agents with map-based policies. We aim to re-enable these generic agents. In early experiments, we noted sample inefficient learning and no incentive to explore its environment as key failure modes of the baseline. The neural agent is not endowed with neither the tools nor the incentives to perform ObjectNav. To remedy these problems, we make a few modifications to the standard CNN and RNN architecture. The architecture is overviewed here. It still embeds observations on the left and aggregates them into recurrent cells in the center. However, the central recurrent cells are split instead of using a large RNN, as this was shown to be effective for incorporating multiple auxiliary tasks in PointNav. This architecture was used to improve both success and efficiency over prior state-of-the-art. Towards success, we first use 6 distinct self-supervised auxiliary tasks. These tasks build environment and action models and thus improve sample efficiency. We also incorporate semantic features, both directly through semantic segmentation that is either provided through ground truth or with a RedNet prediction model, and through a semantic goal exists feature which indicates how much of the frame is occupied by goal categories. In analytic policies, for example, similar features are used to explicitly decide when to navigate towards a cited goal or when to explore. Note that during most of training, we use ground truth segmentation from the dataset. We also use a count-based exploration reward to encourage the exploration skill that is critical to ObjectNav. The default reward, which only encourages progress towards unseen and unknowable goals, is much harder to learn with. Notably, however, adding coverage reward can cause the agent to dawdle instead of stopping appropriately, since it wants to keep exploring. To counter this, we attach a second policy, which only receives ObjectNav rewards and learns off policy throughout much of training. Eventually, we let this tethered policy act and learn on policy for a short period of fine-tuning. Here we show our agent successfully navigating towards the couch in the environment. Note that this policy was provided the exploration reward and goes around the ottomans instead of stopping first at the couch. Next, we consider the tethered policy, which only receives the ObjectNav reward. This agent stops directly at the couch, raising navigation efficiency. We next consider how our agent fails. In our full work, we discuss semantic segmentation failures in addition to agent reasoning and planning failures, but here we focus on semantic segmentation. Here we show the same 6-action agent performing the same episode with and without ground truth segmentation. In this first clip, we see that the agent navigates successfully to the counter. Naturally, providing RedNet segmentation instead of the ground truth to the agent does appear to degrade performance. Interestingly, when we observe the 6-action agent with RedNet segmentation, it appears much more sensitive than 4-action agents are to the same transition, qualitatively becoming much less consistent and skillful in its movement. Quantitatively, even though 6-action agents are better than 4-action agents with ground truth, 4-action agents beat 6-action agents when on RedNet segmentation. However, upon fine-tuning the agent with RedNet segmentation, the 6-action agent again beats the 4-action agent. This rank reversal suggests that this vulnerability to unstable segmentation is in fact an artifact of the learning process, even preferential when attempting to learn a skillful ObjectNav policy. This suggests we need to find ways of robustifying neural agents to noisy semantics beyond what a GRU is naturally capable of. Thank you. Please check out our paper for other analyses.